Good morning, friends. Rushti sir again today with a new lecture in the last in the series, that is electromagnetic induction, the time varying magnetic field. This is a critical problem, part 3. My credentials, note it. The last lecture I discussed some critical problem where the magnetic field, which is uniform in a cylindrical region, and getting switched off. Okay, so during switching off period, that is the decreasing from B to 0. So it's a time varying field. Whatever maybe the switching off time, maybe a microseconds or something. But this is a situation which I am discussing, which is more general in nature. The magnetic field is not uniform in the area. Over the area is not uniform, but it is symmetrical about axis of the cylindrical region. From 0 to R within this region, the cylindrical region, the symmetric B exists. A cylindrical non-uniform magnetic field exists in this, which is symmetric about the axis of the cylindrical region and points along the axis of the region. That you can see. This radius R, are you observing that this within this region the magnetic field exists, which is symmetrical about the axis of the region. OZ is the axis of the cylindrical region, pointing into the plane, and B also pointing into the plane. But B is symmetric about the axis. You can see B is equal to B naught 1 minus R by capital. Here I am writing that also, where B naught is the magnetic field at the axis of the cylindrical region R. Cylindrical region radius is R. Small r is the radial distance from the axis of the region, which is less than capital R. Okay, so that when small r is equal to capital R, B becomes 0, and beyond that B is 0 itself. So I'll say here B is 0. I'll also write that so that you should not have any. B is 0 at R greater than capital. Okay, very nice. This is the question. Now a uniform non-conducting disk of mass n, the bigger circle is the disk whose mass is n. Right, the mass is n, the radius is 2r. That's what I have written here. Mass n, radius 2r, is uniformly charged with charge q. Total charge is capital Q of the disk, and is placed coaxially in the cylindrical region. If the magnetic field is switched off, then find the angular speed of the disk. Okay, remember the two issues here. The major issue is that it is not a uniform B. It is a function of radial distance from the axis, and the disk is covering the complete cylindrical cross section, that circular cross section of the magnetic field, plus going beyond that also, because the radius of the disk is 2r. If you see this, radius of the cylindrical field is R, and that two green lines which I have shown you, these are arbitrary radius small r, which one is greater than R, one is less than R. These are the non-conservative electric field which appear during the time in which that small time duration when the magnetic field is switched off. Okay, so if this B pointing into the plane and the getting switched off, so the ENC should appear in clockwise manner, as you can see here. Okay. It's a non-conducting disk, so charges are fixed to the disk. So in this case, we have to take two regions. One is R less than capital R, and the second region is R capital R, that is the region beyond R to 2R. Here what I am writing, B is writing sigma is the charge per unit, uniformly charged disk, charge per unit area, that is, so then total charge Q will be sigma into pi into radius is 2 capital R square. So 4 sigma pi R square is the charge. Yes or no? So then first find the torque on the disk about the OZ axis due to the force and charge in both the regions. Okay. Why the force comes? Because now see case R, case 1, R less than R. Due to the changing magnetic field during the switching off, the concentric non-conservative electric field appears in clockwise direction as per the Lenz's law. See the green circle which I have shown you in this diagram. This inside the field inside the cylindrical region. This is inside the magnetic field region. This is outside the magnetic field region. Okay. So we know that if the magnetic field in the cylindrical region is non-uniform but symmetric about the axis, that must be, that is, I should underline that. I should underline this, but symmetric about the axis. Okay. Also on time varying. Then the non-conservative electric field ENC is given by, which will be concentric circles, which will be given by R by 2 d B average by dt. B is the area average of this symbol, is the area, the average, this area average of the magnetic field within the radius small r, when R is less than capital R. When R is greater than capital R, then that becomes R square by 2 small r d B average by dt, and this B average, the area average of the magnetic field within the radius capital R. Capital R can be within that, whatever the average value, that average value I am writing in the second situation. This is the average value of B within the radius smaller when R is less than capital. So these are the two things you must be knowing from your basics of electromagnetic induction in a time varying magnetic field situation. So case 1, R less than R, B average is what? B into 2 pi R dr, 0 to small r divided by pi R square. B you write as B naught 1 minus R by capital R 2 pi R dr, then divide integration 0 to any arbitrary R less than capital divided by pi R square. So this gives you this, integration gives you this. So this is the B average within R less than capital R. Then what is the torque? You take a dq element somewhere. I'll take a dq element. For example, let me write this dq element. dq element here, and then dq element here. Okay, this is my ENC. dq into S element. Okay, in both the regions I am showing you. So dq element here. So let me write this torque. dq element ENC, that the force, tangential force into R small r is the torque. So what is dq element? That is sigma into 2 pi R dr, that small elemental ring of radius R less than capital R. Then R by 2, then the B naught, that is the ENC, already I have written this. ENC is, ENC how much? R by 2 dB bar by dB average by dt. So that is ENC R by 2 dB average by dt will be taking the derivative, this is r by 2, 1 minus 2r by 3r dB naught by dt. This is dB average by dt into r. This is the ENC into dq into r. Okay, dq is sigma into 2 pi r dr. That's I wrote here. ENC, that is the ENC is dB average by dt, d by dt of this value, that is 1 minus 2r by 3r into b naught, so dB naught by dt, r by 2. Okay, so that is r by 2 dB average by dt into dq into r. So that turns out to be sigma into pi r cube, sigma into pi r cube. Just open this bracket, sigma into pi r cube dr, then again 2 by 3 pi sigma by capital R fourth by into dr. Okay, into dV naught by dt. I took common outside. Then again I take pi sigma common outside. So RQ dr minus 2 by 3r r fourth dr into dV naught by dt. This is torque, elemental torque along OJ. The total torque from 0 to capital R will be pi sigma is integrated this. For any radius r within capital R, the torque will be this, but it 0 to r dV naught by dt this. And for the region 0 to capital R, I put capital R here. The torque OZ will be sigma pi capital R fourth by 4 minus 2 sigma by 15 pi R5 by R means R4 dV naught by dt. Total charge how much? Q is sigma into pi 2r whole square. The radius of the disk is 2r. So 4 sigma pi r square. So I want to express in terms of total charge. So torque OZ will be sigma pi r square into r square by 4 into 2 by 15 sigma pi r square into r square dV naught by dt. So sigma pi r square is q by 4. So replace that. Q by 4 r square by 4 minus 2 by 15 q by 4 into r square dV naught by dt. Okay, then q by 4 r square you take outside. So 1 by 4 minus, that is 2 by 15. Right? 2 by 15. Q by 4 r square took out, 1 by 4 minus 2 by 15 into dV naught by dt. That is nothing but 7 qr square by 240 into dV naught by dt. This is the torque in the which region? 0 to capital R. Then we go to case 2, R to 2R region. So using equation 3, कौन सा equation 3 बाबू? Equation 3 जो है, this is where equation 3 is B average at any radius R 0 to capital R is this. But what is the ENC for the outside the capital R? This much dB average. That is B average what? The area average of the magnetic field within the radius capital R. So within the radius capital what B average? Put capital R here. So that is B naught 1 minus 2 by 3 or B naught by 3. That's exactly what I'm writing. Use equation 3 for R is equal to capital R. B average is B naught 1 minus 2R by 3R. That is 2 capital R by 3R. So B naught by 3. So ENC will be, now it is outside. So from equation 2 you can see this. Equation 2 gives you R square by capital R square by 2R dB average by dt for ENC. Okay, and B average already for the capital R radius, I already B average I found, putting capital R here, that is B naught by 3. So quickly we go through. So ENC is R square by 2R dB average by dt. R square by 2R dB average by dt 1/3 dB naught by dt. Very simple. This is simpler. Okay. So d torque is the component of torque, elemental torque along OZ due to the outside region. What I will get? dq ENC into R. This dq. See the diagram. This dq. Earlier was that dq, first case one. This dq into ENC into small r, which is greater than capital less than 2r. Okay, that's what. Now this r and r into ENC, r get cancelled. So I get dq r square by 2 1/3 dv naught by dt. So as you observe here in lecture 2 also it told you for the outside region, the torque does not depend upon the small r as discussed in part 2 of this lecture series. So that's why it makes it much simpler. So the torque OZ will be, just take integration r square by 2 dq, that is 1/3 dv naught by dt into just dq integration. So dq integration is total charge q from r to 2r region. So r square by 6 dv naught by dt. R to 2r region, what is the area? Pi 4r square minus r square into sigma. So this becomes 3 pi r square sigma, r square by 6. So then I write sigma pi r square, as you can see here. What I wrote, sigma pi r square, q by 4. So q by 4. So q by 4 I wrote here. Sigma pi r square q by 4. So 3q by 4 r square by 6. This is q is 4 sigma pi r square. Because of that I wrote sigma pi r square is q by 4. So this becomes 1 by 8 q r square dv naught by dt. So total torque OZ total will be how much? Due to the inside charge region, outside charge region. So I have to add this equation 4 and equation 6. So adding this, I get qr square dv naught by dt common. So 7 by 240 in equation 4. Yes, 7 by 240. Then here it is 1 by 8. So 30 by 240, 37 by 240 qr square dv naught by dt. The total torque. So torque OZ into dt from this side if I multiply, so that becomes dLOZ. LOZ is the component of angular momentum along OZ. Okay. So that is 37 by 240 qr square dv naught. Now integrate both sides. Delta LOZ will be 37 by 240 qr square delta V naught. But the delta change in B naught is B naught. Change in LOZ is LOZ only, because initially it was 0, now it is LOZ. Initially it was B naught, now it becomes 0. Change is B naught for the magnetic field. Change is LOZ for the angular momentum. But angular momentum is IOZ into omega, because it's a fixed axis rotation along OZ axis. So omega, that is equal to 37 by 240 qr square B naught. So IOZ is half m 2r whole square into 37 by 240 qr square B naught. So this becomes 4 for 2. So 2 here, 37 by 480. So omega is omega value is 37 by 480 q B naught by m is the omega. So that is the answer. Okay. So this is a very extremely important question, and this angular momentum is obtained by the disk out of what? Out of the angular momentum stored in the electromagnetic field before it is switched off. That's what I wrote in the note. So you see this type of questions, this is a rod they could have used also, extending from axis to the beyond the radius of the magnetic field. Maybe length of the rod could have been 2r. Then similarly we could have done this, much simpler. Once you have done this, that will be still easier. Yes or no? So I think you can go through this again and again, get your points clarified. I will be stopping this series right now, because this I have these examples will clarify all your difficulties, all your doubts, and any such questions in this where whatever they ask, you will be able to answer. Okay, as long as the field is either uniform or it is symmetric. Okay. Non-symmetric field, it is not possible to find like this. Okay, fine. And one more thing I want to point out, if it is not cylindrical field, then only other case which I can handle this situation in this manner, if the field is of infinite radius. If the field is infinite, exists in infinite region, and so the outer boundary makes of the field makes no difference. Okay, so I think you are clear now about this question. So this is my as I told you in the beginning, this is our critical problem part 3. I'm sure, since obviously these are not there discussed in your books or anywhere, so you now will have a clear-cut idea on this time varying magnetic field. If you have understood this, then I am very happy. Otherwise, you go through again and again, and in the case you don't still have not much clarity, then you can contact me. We can discuss, or we can set up a time for a discussion. Okay. All the best to you. Have a nice day and prepare well for your upcoming board and entrance examinations. Don't worry, sky will not fall if you do badly also. But if your concept is clear, you will simply not do badly. I'm sure of it. All the best to you. Thank you all.